Welcome everyone to New South Wales DPI Dairies webinar number 16, Optimizing Milking Management at a Quarter Level. My name is Nicholas Lyons. I am a Development Officer Dairy within the New South Wales Department of Primary Industries. But this webinar today is not about me. I would like to introduce Dr. John Penry. John holds a Bachelor of Veterinary Science and a Master's of Veterinary Studies from the University of Melbourne. John has worked in the dairy industry both as a practicing vet and as an industry consultant for over 20 years. He's got experience as a developer and trainer in many of the national dairy programs in Australia, such as Countdown and INCALF. He did his PhD at the University of Wisconsin-Madison, conducting milk harvesting research with Professor Doug Rainman and Irish postdoc Dr. John Upton. He then did a research and advisory role back in New Zealand, and he's now Manager, Technical and Innovation at Dairy Australia. It's great to have John on board and share his knowledge and his experience with this topic. John did a short presentation for the AMS farmers as part of our annual meeting, and I thought he had great insights that could be valuable to the rest of the industry. So I've invited John to come on board today and share some of his work done as part of his PhD on milking management at a quarter level. So John, thank you very much in advance for your time, and the stage is all yours. I'll give you presenter rights now.
So thanks very much, Nico, for that introduction, and irrespective of where you are, it's either good afternoon or good morning, and I'm really glad that people have taken the time to have a look at this. So we're going to go for about 45 minutes and give ourselves some time for questions. So let's see if we can get the technology to work. Don't want to add anything else into Nico's very kind introduction, other than to say he's been most generous with the amount of time I've been in the dairy industry. I'm about to crank through 30 years working in the dairy industry in the various things that he's outlined, and it's amazing how 30 years goes past in the wink of an eye. Okay, so off we go. And just trying to, right, okay, here we go. All right, so what we're going to look at today is really...
Sorry, John, I think we are not seeing your screen. I think you need to share your screen.
Sorry, I beg your pardon.
That's fine.
Is that better? Okay.
Way better.
Sorry about that. Technical glitches 101. Okay, so folks, what we're going to do is we're going to look at some aspects of research that I was involved with between 2014 and 2016. This research was conducted both at the University of Wisconsin in Madison, but also at a commercial farm, which I'll outline in a moment. My boss at the time was Professor Doug Rainman, widely acknowledged to be probably still, I think, the premier milk harvesting scientist in the world. I was fortunate enough to work out of one of the very few laboratories left in the world within a university that deals and researches with into milk harvesting or milking machines. For those of you that are students of history, this lab was started in the early 90s by Graham Mean, who some of you might know. He's an Australian who is probably the most famous milk harvesting scientist that there has been, certainly in the last 50 years. So I was very fortunate to be involved in a program of research there that not only looked at how we might optimize particularly liner performance, but some aspects of how that might flow onto automatic milking systems. Okay, I always start with this slide. It's just to remind us of where we've come from. On the right-hand side of the slide is a diagram. This is actually the patent produced in 1903 by a fellow called Alexander Gillies. He was a dairy farmer in Western Victoria at a place called Terang. And this is the patent for the air admission hole that is still part of a conventional milking cluster to this day. And the reason why I put it up is because the fundamentals of machine milking using a twin chambered teacup really haven't changed that much since about 1895. But what has happened is the types of ways that we apply that base technology has altered dramatically. So from the time when this patent was done in 1903 through to 1992, when the first automatic milking systems emerged in Holland, we've come an enormously long way. So I use this to sort of anchor us in history. We've come an enormous distance in a relatively short period of time. So this is about milking management at the quarter level, and specifically thinking about how it applies in an automatic milking system, but it's worthwhile just defining our terms first. So when I talk about milking management in this context, I'm talking about three things: milking speed, milking gentleness, which is different to milking comfort. So milking gentleness, gentleness on the teat tissue, and milk production efficiency. And just to try and be a little bit more specific, I'm going to put these descriptors next to those terms. So milking speed is defined as kilograms of milk per minute. You can substitute litres for kilos, but kilos of milk per minute is what I'm going to use. For gentleness, the types of things we describe are congestion of the teat skin and teat itself. We can describe the turnover of keratin within the teat canal. And we can also describe how the gentleness of the way we milk the teat and teat tissue can either increase or decrease new infection risk. And milk production efficiency is about how we milk a cow and how that impacts on her ability to produce milk in a quarter per hour between milkings. So that's how well does the milk get produced within a quarter between milkings. And that's how we're defining milking management for this context. So you can ask the question, why would you bother focusing in on the quarter? Well, it makes sense if you're dealing with an automatic milking system because they are truly quarter milkers. But beyond that, there are some physiological reasons why you might do that. And some of them are things like the teats are actually individual in their anatomy within a cow. And more fundamentally than even the teat anatomy, the response of the quarters to how you milk is truly an individual response. So you've got 4 quarters which are connected in some physiological ways. For example, they all see oxytocin at the same time during milk letdown. But in many other ways, the response of the quarter and how it responds in milk production, for example, is truly a quarter-based response. So they have a local hormonal environment which is regulating them at the quarter level, not necessarily at the whole of udder level. So that's why it's important to think about focusing on the quarter as the unit of study here rather than the udder. The other reason why we want to focus on the quarter is because of the milk flow characteristics of the quarter, and the production characteristics can be quite distinct. So up here on the screen, we have a quarter milk flow curve. So each one of these different colors represents a different quarter. And it doesn't really matter which quarters are which in terms of the colors. What I'd like you to focus on is the fact that you have on the vertical axis, you have milk flow rate in kilos per minute. So that's from 0 up to 2.6 kilos per minute. And down on the horizontal axis, we have a time scale. Don't worry about the numbers not appearing to make a lot of sense. It's just time. That's the way to think about it. But if you went from the left-hand side of the graph to the right-hand side, it represents about 5 minutes. And the thing to understand here is that the height at which each of those individual coloured line reaches, that shows you where the peak milk flow positions itself for each of the quarters. And it also shows you how long those quarters milked for before they stopped milking. And you'll note that for both the black and the red lines, you get quite an abrupt change from peak milk flow, where the curve flattens off or plateaus, to when it decreases, and it decreases quite suddenly. So what is typical of many milk flow curves is that the quarter will go from peak milk flow to very low or no milk flow in the space of 5 or 6 or 7 pulsation cycles. That can be quite typical, particularly in a well-prepared quarter that's had an oxytocin release before the teat cups go on. So this is designed to show us 2 things in essence. The first one is that milking time will vary between quarters within a cow. And the other thing is that the milk flow rate at the peak will also vary between quarters within a cow. The other thing, just to complete this picture, is the hatched line. The hatched line sits underneath the red line. And when you look at the total area taken up by that hatched line, that's the way you calculate the milk volume or milk yield for that red quarter. So in the space of one graph, we have represented what's the peak milk flow rate for that quarter. We have represented what's the total milking time for that quarter. And by looking at the area under the curve, we can calculate the total volume or total yield in kilos or in litres. There's a couple of other key things that I think are worth mentioning about AMS versus conventional milking. Conventional milking, by that I mean that you have 4 teat cups connected to a bowl to create the cluster, and that the teat cup removal process is happening at all 4 teats or all 4 quarters at the same time. Now, automatic milking systems or milking robots are different to that. And they're different basically for these reasons. The first one is that we have, because of the programmed mechanical nature of the pre-milking preparation, it's very standardized between teats and between cows, because we have taken out the human variation in how teats are prepared prior to the teat cup going on. So that means that they have a relatively standardized or consistent oxytocin release between teats and between cows, cognizant of the fact that oxytocin release isn't an all or none thing. There is some biological variation around that, but by and large, pre-milking preparation is consistent. The second thing is that this is truly quarter-based milking. So there is no bowl that the milk is going into. And as you can see from the third point, the detachment of each teat cup is based on a quarter milk flow rate. It's not based on a composite udder milk flow rate, it's based on a quarter milk flow rate. So truly quarter-focused milk harvesting. The other thing that also happens with an automatic milking system is the cows basically set, by and large, their milking interval. And just to anchor you to where the research sits around this, has been quite a large body of work done since the mid-1960s that basically tries to explore, mostly through conventional parlours, tries to explore what happens if you take cows from twice a day milking or 2x up to 3 times a day or 4 times a day, or indeed drop them back to 1 times per day. And to summarise the research, this is essentially the story. If you take on average an animal, especially in early lactation, and on average, instead of being milked twice a day, she gets milked 3 times a day, the increase in milk production rate is about 15 to 20%. And if you then go from 3 times a day to 4 times a day, the increase in milk production rate is again another 7%. So this is a physiological response. As you increase the quarter more frequently, so you're increasing milking frequency, what happens is that there is a physiological response to slightly alter and increase milk production rate. And we see that evidenced through the increased milk yield. And we all know that cows in an AMS system, by and large, set their own milking interval times. And in a lot of the research, what has been found is that when AMS units are put in place, and a herd might have been previously conventionally milked twice a day, the milking interval goes up often to 2.5, 2.8 milkings per day, something of that order. Okay, we're now going to specifically look at some research, and this is just to anchor ourselves geographically. The red box on the left-hand side of the map of the United States is centered around Madison, which is in the state of Wisconsin in the Midwest. The research, however, was done on a farm in Pennsylvania, at a place just outside of Gettysburg. So that's the square on the right-hand side. More specifically, it was on the border between Pennsylvania going down into Maryland. So that box is right in the middle of where Gettysburg is. So this is the farm. The farm is called the Mason-Dixon farm. It's a very unusual farm in many ways. One of the ways that it's very unusual is that this farm is very old. It was settled just after the War of Independence of the United States. This farm is a family-owned farm. They now have their 9th generation of this family operating this farm. So truly remarkable. The red square or the red rectangle on the right-hand side shows you where the robotic barn is. And for those of you that are looking at that diagram closely, you'll note that we have essentially 20 pens marked up on that map. So a very long barn, 20 pens inside that, and we'll see this more closely in a moment. The rest of the farm is a pretty standard setup for a conventionally milked housed herd in the United States, housed in free stalls. So this farm essentially has 2 arms to it. It has a conventionally milked herd, and it also has a robotically milked herd. The person on the right-hand side in this photo is the person that I worked with. He is one of the 8th generation on this farm. His name is Doyle Waybright. Absolutely terrific fellow who is interested in on-farm research. So he has worked with the University of Wisconsin on and off for quite a few years. And he and the team of people that work in this farm were very gracious in allowing us to have very wide access to not only information and data from this farm, but also to run an experiment as well. To give you a sense of what the barn looks like, it's pretty unusual to see sawtooth roofed designs in Australia. It's relatively uncommon in the United States too. Because of where this was, this milking or housing area has to have the ability to lower blinds down the side. So whilst the walls are open here, they do have the ability to be closed off because of the winter. And exactly the same thing happened with the vents that were sitting in the roofline. Here we see another view. This is just showing where the milk collection area was and where some of the componentry around milk cooling was kept. This gives us 2 views. These are sort of landscape or wide angle views. So this is looking, the bottom picture is probably the first one to look at. It's looking directly down this barn. And what you can see off to the right-hand side, you'll just see a small blue area that represents one of the milking robots. The way this farm was set up was they had 20 pens, and each of the pens had 1 robot or 1 AMS unit. So unlike a lot of other setups where they have multiple robots or 2 robots per pen, this farm had elected in their design to have 1 robot per pen. On average, there were 55 animals allocated to each robot. They also had it so that all of the first lactation animals, or all of the heifers, were grouped together. So there were 6 pens of the 20 that had heifers only, and of the remaining 14 pens, they were all mixed age animals other than heifers. So there was second lactation and upwards. The way they organised their calving pattern was it was year round. So as animals calved and came into the herd, they were evenly distributed amongst the pens, so that on average, the average lactation number of days in each pen was about equal. So there was an equal mix of fresh cows, mid-lactation cows, and cows in the later part of their lactation. This herd also, interestingly, had a mix and match of traffic flow systems. So in some cases, they had traffic or guided traffic flow, but in about 5 of the pens, they had no guided traffic flow at all. So it was the robot who was doing the traffic maintenance, and they actually preferred that system because they found that the cows turned up to the box more often. The milking permission, just to outline, was based on time only. So if you were a heifer or a first lactation girl, as long as you had been away from the box for more than 5 hours, you were given milking permission. And with the cows, as long as you'd been away from the box for 6 hours, you were given milking permission. There were no milking permissions based on production at all. So let's have a little bit more of a view of this setup. So again, here's the freestall setup. It was sand as the bedding on rubber mats. So they use both a combination of fresh sand and recycled sand, pretty standard for a freestyle dairy in this part of the world. And again, that image up on the left-hand side, you can see a structure like a room, and in that room are 4 milking robots. And again, 1 robot per pen, but the robots were clustered, so there were 4 together. Here's another view of, well, a close-up view of that structure housing the 4 robots. We can see one of the robots just off to our right-hand side. This property all had 1 type of robot. It just so happened it was a de Laval. And you can also see in this instance, this part of it had a guided traffic area, but for the most part, they determined that non-guided traffic was a better option for this herd compared to guided traffic flow. Okay, one more shot, just going straight down the alleyway. The feeding areas are off to the left-hand side, so they're on the outside of the building, and the loafing areas are down the middle side, and the robots are clustered in the middle. And finally, just wanted to show you a couple of shots to see how logistically they had set this farm up. One of the real challenges here is because all the milk was going to one central location. In fact, there was only 1 plate cooler, and then they were putting it straight into trucks, so it wasn't going into a vat. One of the big challenges of this farm is how do you set up your milk supply pipes, taking milk from each of the robots through to where the pickup area was. How do you do that in a way that not only do you deal with thermal expansion of the pipes, but you also deal with how you clean those pipes as well? And they had set up a system. Let's just have another look here. They had set up a system of a large alleyway running down the entire length of this long rectangular barn, and they'd organised it such that the cleaning took place in components of the barn. So they didn't try and clean all of the lines at once. They were on a system where the robots were taken off for a certain period of time, and they would clean them in a group of 4. But it really was a pretty large engineering exercise to get the milk delivery component of this dairy to work. And they certainly challenged the design concepts, because up until this point, not many people had installed much more than 2 to 4 robots in the United States, and in this farm they had 20. Here's just a shot showing you milk going straight into the tanker and through a very large plate cooler, which was being used. It had propylene glycol going through it rather than water. So no vat, straight into the tanker at about 6 degrees, 4 to 6 degrees, and straight off to the processor. This is one of the final shots just showing you what this farm was doing. The reason why I put this up is it's really interesting how this farm viewed performance of the robots relative to each other. And I'm just going to highlight here in red the milkings in the last 24 hours. The way these robots were set up was that they had to be offline for cleaning 2 hours of every day. So they had 1 hour of downtime every 12 hours. And one of the things that they were really quite tight on was the amount of idle time of the box. The way they had positioned themselves with their stocking rate was they wanted to have the box idle time at about 15% of available time, 15 to 16%. So that meant that in every 12 hours, if there was 11 hours where the box was available for milking, they only wanted the box used in that 11 hours for about 85% of the time. And the reason why they set it up that way was they said if they pushed the system too hard beyond 84 to 85% of utilisable time, what happened was if there was ever a breakdown, it was very, very difficult for them to keep the production system in place. So if there was a breakdown, they had to redistribute those cows for a short period of time. And whilst they were very good at doing their own repairs and maintenance, it became challenging for them to maintain workflow, and particularly cow flow, if they had an increased box utilisation time of more than sort of 84 to 85%. And they really did monitor this very well and very closely, and that's the reason why the stocking rate was 55 cows per box and not more than that. Okay, so I think we've covered off on most of this. For those of you who are interested in what types of production this herd was doing, the herd average per lactation was around 11,200 kilos or 11,200 litres. We've already covered off on the number of animals per unit. We've covered off on how they were grouped. Finally, though, and importantly, we had access to 1.5 years worth of records coming from the robot. And so there was something in the order of 1,500 cows in the analysis. We were getting about 90,000 milking records per month. At any one time, there was around 1,100 animals being milked in this barn. So one of the questions that we initially asked was, given that we have a beautiful set of data from these robots, where at both the cow and the quarter level, we were measuring things like flow rate, both average flow rate and peak flow rate. We were measuring yield at the quarter. We knew exactly what time each of the milkings occurred for an individual animal, and we did know how long they spent in the box. We didn't know what the cup attachment time was. We had to calculate that. But we were certainly able to calculate things like milk production rate between milkings for an individual cow. So one of the things that we're able to do with this type of rich data, we've got multiple points of measurement at the quarter level across an entire lactation, is we can start asking questions around, are there cow level factors that might influence things such as milking speed and quarter milk production? And that's where the starting point was for this piece of work. So let's now have a brief look at some of the things that we discovered in this herd. The first one is, if you have very consistent cow preparation prior to the teat cups going on, very consistent quarter preparation, you tend to get a very consistent oxytocin release. And with that, what happens is you also have a high degree of association between quarter peak milk flow rate, which is on the left-hand side on the vertical axis, and quarter average milk flow rate. So recall that peak milk flow rate tends to plateau in most quarters. They go up to a peak very quickly over about 30 seconds, and then they sit at the peak by and large until they come off the peak again quite quickly. And unlike what you can sometimes see in conventional milking herds, where the consistency of teat preparation might be quite wide, here we have a very tight association between quarter peak milk flow and quarter average milk flow, which means you can use one to predict the other. If we then move on and say, well, if we're interested in how peak milk flow at the quarter level might be influenced by things other than the settings of the milking machine, so other than things like what vacuum or pulsation settings we have, are there things that we can discover? And one of the things we can discover is there is some variability in peak milk flow rate depending on how often the cow tends to turn up to the box. And the story here is essentially on the left hand, on the vertical axis, we have peak milk flow rate. And on the horizontal axis, we have average milking interval for a cow. And what we're basically saying here is, on average, if the cow likes turning up to the box every 6 hours, and there were certainly animals in this herd that was their tendency, on average, they tended to have slightly lower peak milk flow rate than cows who turned up to the box, say, every 12 or 14 hours, for example. And one of the things we can do with this information is we can start to factor in how we might potentially alter box settings into the future. And we'll come to that a little bit later on. Moving on from there, there has often been the question, or it's almost posed as a truism, certainly when I was doing my training many years ago. And the conversation went something like this: cows that have high milk production tend to be fast milkers. The problem is that that doesn't really hold water when you actually analyse it at the quarter level. So on the left-hand side of the graph, on the vertical axis, we have quarter milk yield from 0 through to 8 kilos per milking. And on the horizontal axis, we have quarter peak milk flow rate from 0 up to a maximum of around 2.75 kilos per minute. And you'll note that it looks like a shotgun blast on the graph. And you'll also notice that whilst we have put a black regression line through it, it has a low, what's called an R squared. So essentially what this means is because we don't have the points clustered around a trend line, what it means is there is very weak association between quarter milk yield and quarter peak flow rate. So in essence, the way we interpret this is to say, if you know what the quarter milk yield is, it doesn't mean that you're going to do a very good job. It means you're not going to do a very good job of predicting what a quarter peak milk flow rate is. So that old truism of large milking quarters milk quickly, it's not a very good truism, and I wouldn't hang my hat on it because you can't predict it. This has implications for attachment order, and let's just work through this. So if you look at, as we've just said, quarter milk yield and peak milk flow are poorly associated, and because there's a tight correlation between peak milk flow and average milk flow, you can also postulate that quarter milk yield and average milk flow are also poorly associated. However, we do and we can measure quarter milking time. If you know what the yield was and you know what the average milk flow rate was, and that's what's measured on this particular type of robot for each quarter for each milking, you can calculate what the quarter milking time is. So one of the things we did was, because in this setup on this farm, the attachment order was done in a way that it was fixed. So depending on whether the arm was a left-hand armed box or a right-hand armed box, the attachment order was always exactly the same. So it didn't take into account quarter milking time. So what we did was we divided the cows up. We determined, based on assessment of how they currently milked, we determined the cows who, it just so happened, let's just bring it up, it just so happened that we could find the cows where the shortest quarter in terms of milking time was attached first, but the longest milking quarter was attached last. So we called this suboptimal attachment order. And what we did was we compared those cows with cows where, purely by the way that they actually milked, the longest milking quarter was attached first and the shortest milking quarter was attached last, which we termed as optimal attachment. And what we found when we did this was we just looked at how much milk did those cows produce through the box per unit of box time, because we knew how long they were in the box for, we knew how much milk they made. And what we discovered was when you attach according to putting the attachment first onto the longest milking quarter compared to putting it on the shortest milking quarter first, we found that there was a change in milk yield per unit of box time by something in the order of 58%. And this was really a revelation to us because as far as we knew, no one had looked at this in the past. And what it basically told us was, if you can get the technology such that you can attach in logical order of longest milking time to shortest milking time at the quarter level, you have cows in the box for less time and you harvest more milk per box per hour. And it's not a small effect size, it's quite a significant effect size. It's a large effect size. So this was really a revelation to us. There were some other things which were curiosities that we found in the research, some things we can't explain. So again, this graph, let's just orient ourselves. On the vertical axis is peak milk flow rate at the quarter level. And on the horizontal axis is days in milk, from 0 days in milk through to 300. And you'll see that there is on the graph, it's like an S pattern or a sigmoid pattern. And basically what it says is on average across all animals in this herd and across all quarters of all animals in this herd, we see a decrease in peak milk flow rate at around day 50, and then it goes up again and peaks again at around day 150, and then it decays again down to about 300 days. Now, we've been pondering over this for literally years now, and we haven't been able to explain it. This was the first time it was ever reported, and we can't explain it. So if anyone has any great ideas as to what could be underpinning this pattern, which we see for all quarters and all ages in the analysis, I'd be very pleased to hear your thoughts, because we certainly haven't been able to crack the nut on this one. One of the other things that we were able to ask in this research is if quarters are producing milk differently, so they have different milk yields within a cow between the quarters, one of the questions which flows on from that is, at the start of the lactation, do the quarters rank themselves according to highest to lowest milk production? And do they then stay there at the same ranking? And again, no one had ever asked this question before. So here was the perfect opportunity with a large data set. Again, more than 1,500 cows over a lactation and a half in many cases. And what we discovered was there was only 10% of udders, 10% of udders where the ranking of the quarters for milk yield did not change over the course of the lactation. For the majority of udders, you either get 2 quarters changing rank at least once, or you get all quarters changing rank at least once. And this was after we had taken all of the mastitis cows out of the analysis. So there's no cows with clinical mastitis in this analysis at all. And this was, again, a little bit of a revelation to us, because you think that having established the lactation, the quarters are very much set in terms of their ranking, or at least that's conceptually what we thought, but that's not the case at all. And the type of change that they had to have in order to change rank, we had set it so that it was sitting around 0.25 of a kilo within the quarter. So it's not a small change in milk production. So the quarter ranking is quite volatile and changes a lot over the course of the lactation. The other thing which also flows on from that is this, again, it's a bit of a truism around, well, the front quarters produce 40% of the milk and the rear quarters produce 60% of the milk. The trouble is that whilst that is an okay thing to describe, it's only true for 3/4 of the time. So what this slide shows us is that we ranked the quarters each 10-day average according to which was the best producer through to which was the worst producer. And what we discovered was that in essentially 23% of the time on average, a front quarter was either the best producing quarter or the second best producing quarter in terms of yield. Rear quarters tend to be better on average, but 1 out of 4 times there's a front quarter who's doing either the best production job or the second best production. Again, a bit of a revelation to us. This just shows how consistent we are from the most productive quarter through to the least productive quarter on average. Don't worry about whether it's a front or a rear. They were relatively consistent in terms of their relative ranking to each other. So the best producing quarter tended to produce about 30.2% through to the worst producing quarter tending to produce about 20.3% of the total yield. One of the other questions we were able to ask out of this is, well, here's the question. If you take the best producing cows in the herd, so the cows that have the highest peak milk when they hit whatever their peak lactation day might be, rank the cows according to which are the best producing cows through to the least producing cows at the udder level. And then the question you ask from that is, what tended to be the characteristic of the best producing cows? Did they tend to have 1 or 2 quarters that were very, very high production and 1 or 2 quarters that were very, very low production? Or did they tend to be quarters that were very even between each other within an udder? And the way we did this was to look at, we measured the variation between the quarters within cow for each milking. And we basically just plotted that against what the maximum udder production rate was. So all of the cows that are represented by a blue dot over on the far lower right-hand side of this graph, they are the best producing cows in this herd. And to cut to the chase, what we discovered was there is no pattern here. So the best producing cows in the herd, some of them had very consistent within quarter production and others were very variable. There was no pattern. So you can't predict based on quarter variability within a cow whether they're going to be medium, high or low producing cows. Again, this was something we were not expecting. We also had the opportunity to explore a research question around if you alter milking interval, particularly in middle of lactation, will you alter milk production rate? And this was based on some previous experiments that had manipulated milking interval early in lactation. And what we were doing is we were trying to replicate this work in the middle of lactation. One of the underpinnings for this is this graph. So on the vertical axis, we have milk production rate. So that's the amount of milk being produced at the quarter level for every hour between milkings. And on the horizontal axis, we've got milking interval from 6 hours through into 16 hours. And essentially what this graph says is if you increase milking interval, so you milk them less frequently, what happens is milk production rate goes down, and it goes down by about 1.5% per hour that you stretch out the milking interval. And this is a physiological effect. One of the things which also sort of sat off to the side of this is the tendency for mature cows, so lactation 2 and above. Those cows were quite predictable. Sorry, this is the graph on the right-hand side. They were quite predictable in terms of as they went through the lactation, they tended to increase slightly, but tended to increase their milking interval, whereas lactation 1 animals on the left-hand side were scattered. So as they went through the lactation from 0 days of milk to 300, it was quite random what their average milking interval was. So with both of these things in place, we decided to look at some cows which were lactation 2 cows, and we basically said, right, if we can alter for some of those cows, if we can artificially alter their milking interval and decrease it by 2 hours for a period of 21 days in mid-lactation, will we see a response in milk production rate? Will we see an increase in milk production rate? We knew that if we did this early in lactation, we would see this, but no one had ever tried to manipulate milk production rate through milking interval in the middle of lactation. So we set up an experiment to do this. And here were the results. During the 21-day treatment period, we took the treatment and control cows on average 10.7 hours between milkings, and in the treatment group we reduced that by more than 2 hours. So during the trial period, those cows were being milked every 8 hours compared to their controls who were being milked every 10.4 hours. And to cut to the chase, there was no difference in milk production rate that we saw in this experiment. So we were expecting that we might see a change, but indeed we did not. So whilst we were artificially manipulating milking interval in the mid-lactation, we did not see a production response. And we think the reason for that is because we were too late through the lactation curve in order to get the physiological effect, or at least that's the working theory. The final part of the puzzle is an age-old question around if you have a high milk flow rate, will you see an increase in clinical mastitis? The underpinning theory behind this is one that basically says if you have higher milk flow rate, by definition, the cross-sectional area of the teat canal when it's open during milking is wider, because in order for the flow rate to be high, you have to have a wider pipe. That's the simple way to think about it. And so what has been thought of in the past through some research that was done in the 80s particularly and early 90s was that if you have high milk flow rate quarters, they tend to be more prone to clinical mastitis, presumably because it takes those teat canals longer to refold after the milking is finished. So we had the ability to explore this theory again with this group of cows on this farm. And so here's what we did. We looked at all of the cows who had their first case of clinical mastitis during the year of 2015, and we matched them up with equivalent cows, in fact 6 equivalent cows, based on milk production and based on days in milk window, etc. And what we did was we tested, did the quarters that had higher milk flow rate tend to be the quarters that had higher risk of mastitis? And here is a snapshot of the clinical mastitis cases, evenly scattered between the left front and the right rear. The mean days in milk was sitting at around between 100 and 175. And here, cutting to the chase, are the results. We found no influence of peak milk flow rate on the risk of clinical mastitis. So that's the variable sitting at the top that says PMF, enrolled quarter. And essentially the way you read this is the odds of having clinical mastitis is not associated with either high or low peak milk flow rate. So certainly in this data set, with this analysis, we could not support the contention that high peak milk flow rate quarters tend to have a higher incidence of clinical mastitis. And folks, that's it. So this is just a brief snapshot through a series of research projects that were done on one farm in Pennsylvania. And I do need to acknowledge the sponsors for this work, which was Avon, which is a milking machine company that produces liners in the UK, Dairy Australia, Chuggas, which is the Agricultural Research Authority in Ireland, and of course the University of Wisconsin-Madison and their Department of Dairy Science and Biological Systems Engineering. To finish off though, I think it's worthwhile just thinking about why should we be interested in this type of research? Because essentially what we've done here is we've looked at cow level factors that might influence peak milk flow rate, and we've looked at cow level factors that tell us about the variability between quarters in terms of milk production, milking time, peak milk flow rate, and average milk flow rate. And I think where these questions naturally land is as we're thinking into the future about how we design automatic milking systems, recall that there's something like 40,000 of these boxes in the world now. And this type of milking technology is probably only going to increase its footprint. What we should be thinking about is how can we alter the engineering of these machines? How can we optimize it so that we are attaching the teacups in the correct order relative to total milking time, predicted milking time at the quarter level? How can we utilize this technology so that we spend no or very little time in the low flow period? How can we optimize this technology so that we get as consistent a pre-milking preparation as possible? And I suppose thinking about it slightly more widely, how can we think about potentially altering at the quarter level vacuum and pulsation characteristics so that we optimize the peak milk flow rate at the quarter level based on measurements that we've done at the quarter level for a cow. So this is, I suppose, thinking not that far into the future about how we might tailor the milking experience for a quarter based on information that we have measured in that quarter for, say, the first 10 or 15 or 20 days of milk, so that we are truly optimizing not just milk harvesting speed, but gentleness of milking and potentially also milk production rate efficiency. So that's it. That's a brief exploration through a piece of research that certainly occupied my brain for about the best part of 2 years. And with that, I just want to finish with this slide, some beautiful tulips from the University of Wisconsin that emerge after the snow has gone away. So I'd just like to thank you all for your attention, and I hope you found this of interest. And Nico, I'm going to hand over to you, depending on whether we've got any questions to address. So thanks, folks.
Thank you, John, for that. I think it was a really good insight into the topic. Certainly, I've learned a lot on these topics, and I think the audience has too. We still have 20 people hanging on, so I guess that is an indication that it was of interest and people were interested in the topic. There's been a couple of questions come through, and I'll just go through them to see if we can tackle them. The first one is, what was the tea preparation routine or tea preparation levels in this farm? And could that have any impact on flows or the likes?
Yeah, so the teat preparation was standard for this type of AMS. So it was a single teat cup that is used only for preparation and is also doubles up as gets used for teat disinfection afterwards. The preparation was done such that between the first tactile touch on the teat skin, because recall that oxytocin release is a tactile response to skin. So the gap between when the teat was first stimulated, tactile stimulated, through to when the actual teat cup for milk harvesting went on was something in the order of 45 to 50 seconds from memory. And for the most part, that is an adequate lag time between when the tactile stimulation finishes and when the oxytocin release and associated milk letdown has occurred. It does vary a little bit according to cows that have high milking frequency or low milking interval will sometimes require a slightly longer lag time. And that is also the case for cows in later lactation. And it's to do with how much milk is sitting in the cistern of the quarter relative to the alveoli of the quarter. And it's just a function of how much milk has free flowed by gravity into the quarter cistern between milkings. It's a really good question.
So do you think, and this is my personal question, but do you think moving forward that could also be a factor that is kind of taken care by the software, like which cows do we stimulate or prepare according to milking intervals and expected yield?
Yeah, I think so. I mean, there's some really solid research that sits behind this that was mostly done out of the University of Bern in Switzerland. So we actually know quite a lot about how milking interval and days in milk intersects with the likely optimal lag time between when a teat is first stimulated with a tactile stimulation and when it's likely that oxytocin release and milk letdown has been completed successfully. So that's certainly something that you could tailor into how the milking robot tackles each cow, because this is actually sitting at a cow response, not a quarter response.
Yeah. No, excellent. There's another question saying, if we can change which quarter is milk first, second, etc., considering the longest versus shortest order changes from time to time, how often do you think we need to revisit this change and manipulate the system to reduce milking time?
Yeah, well, one of the nice things about these machines is they're measuring what's happening at the quarter level every time a cow presents to the box. So you could, in theory, if you're able to get the engineering to work, you could, in theory, alter this after every milking. Now, I think that's sort of taking it one step too far. Most of the analysis that we were performing was done in 10-day windows. So for the most part, you had between 20 and 30 milkings that you were analysing within a 10-day spread for a cow or for a quarter. So I think you could easily make the argument that this is the sort of thing that you would measure across 10 days or across 5 days. But conceptually, you could measure it every time.
Perfect. Thank you for that. There's another question saying, John, would you expect similar results in pasture-based systems, or do you think that some of the seasonal and management differences with pasture-based systems would impact on cow factors and associated research findings?
Yeah, so that's a great question, and I can answer it pretty simply. I haven't shown you this, but we had another data set that came from a pasture-based AMS herd, and whilst we never published those results, I can tell you that they were carbon copies. So that's what really stunned us. We had two data sets from two completely different parts of the world, two different production systems. The commonality was the fact that they were both being milked with AMS, and we were stunned at how the findings from North America were being mirrored by findings out of the Southern Hemisphere on a pasture base? Great question.
Excellent. Those are one of those studies that you decide, I'll do it after my PhD, and then you run short of time. The other question is, while we can measure and then manipulate the system, do you think there's any chance we can predict which quarter will be strongest versus shorter?
No. So the answer is no. You really have to, you've got to measure essentially two things. You've got to measure average milk flow rate, and you have to measure yield. And with both those things, if the machine is not measuring milking time at the quarter level, you can calculate it. But you can't. In our analysis, knowing either milk yield or knowing average milk flow rate, they're not good predictors of each other. So you actually have to measure it, and you can't make assumptions about where the quarters are going to be positioned in terms of milking yield, nor indeed milking time, unless you just go and you have to measure them. And you have to make, you basically have to go in making no assumptions.
Excellent. There's two other questions. The other one is, have you seen any relationship between milking interval and milk production efficiency, but of fat and protein, not only volume?
That's a really good question. That work has been done. It sits in a very nice review paper that was published about 7 or 8 years ago. So the work has been done. I just can't remember what the results were. So rather than opening up my mouth and finding that I said the wrong thing, I'd be very happy to steer you towards the review paper, Nico, and you can pass it on to the person who asked that question. It's a great question. I just can't remember the answer.
Perfect. And the last question is, you said there was no difference between the rank of the quarters across the lactation. Is there any relationship according to milking interval?
No. So let me just back up though. If you take the quarter identifier out of it, so you're not worried about whether it's a front or a rear quarter, all you're worried about is ranking the quarters on average between the best quarter and the worst quarter for milk yield. They are very consistent across days in milk for what gets produced, and that relative ranking, so highest through to worst or lowest ranking for milk yield as a percentage of the total yield tends to be very consistent, irrespective of milking interval or days in milk.
Excellent. Excellent, John. Look, I want to thank you once again on behalf of all the attendees, and thank you for your time and your insight. I think it has been not only a great attendance, but also a great presentation and discussion. So thank you again for your time today with us.
Terrific, Nico. Thank you very much for the invitation. And whilst it's an unusual experience presenting at a webinar, I hope that this very brief foray into some of the science of milk harvesting with the AMS has been of interest to the audience. And thanks to everyone for their attention.
Definitely has, and you did a great job. So thank you for that. So as with all our webinars, this webinar has been recorded and will become available on the New South Wales DPI Dairy website. So for more information, please visit our Facebook page that is followed by more than 1,300 followers from all around the world. We also have a newsletter that goes out 4 times a year to more than 500 subscribers. And we also have an online AMS community. So feel free to join or follow any of these initiatives to stay updated on all the work we do in the area of precision dairy farming and robotic milking. So for more information, I encourage you all to visit the New South Wales Department of Primary Industries website, where you will find the latest tools and resources that will help the dairy industry. There is a specific section on precision dairy farming, which includes a lot of this information and tools discussed today. So once again, thank you all very much for joining, and hope to see you the next time.